Alright, let's start with the background study for our project. So we know that the agricultural sector is one of the major contributors to Malaysia economy. So Malaysia agricultural sectors consists of three main activity, which are crops, livestock, and fishery. Livestock consists of cow, pig, chicken, and so on. Right. So livestock has been one of the most profitable activities in agricultural industry. So we thought that the farm waste-based biogas has a huge potential in energy generation countries such as Malaysia, US, and so on. So moving on to our problem statement, so we know that waste is very unpleasant. So if large amounts of waste is released to the environment, they might cause several pollution, air pollution, odor pollution, or even land or water pollution, which is not good to the earth. So, and then if improper management of pig manure can cause dissatisfaction of local community in Malaysia. So the main objective of this project is to design a facility that can manufacture and process the biochemical product using pig manure as raw material to reduce the environmental issue. Mhm. So we can generate D2PFD and PINID using relevant Petronas standard. We can also conduct safety analysis on the operation and equipment for our overall system, our overall plant. We can also apply fundamental theoretical knowledge of chemical engineering on the conceptual design, on the overall design of our plant, and then also to find out where cost effective process option for our plant. The scope of study for this project is, first and foremost, the most important is that we analyze and research through previous papers and documents found on the internet so that we know what specification to follow. Then the selection of most suitable chemical process road. There are different kinds of process road that lead to the same outcome. So we need to find out which is the best process road for our plant design. Of course, justification on discussion in plant design problem that we face by fully utilizing the software, computerized software such as Icon and HiSys for simulation and design purpose. So application of chemical engineering knowledge such as heat integration and control principle on plant design to make it more advanced, or maybe heat integration we can make it more cost effective. Following that, we can use HAZOP or PHA to assess the safety of our plant. Then lastly, we can conduct economic analysis for the plant overall production that we can see that it's profitable or not.
Hi, my name is Liew Jia Hui, and I'm going to present for the literature review part. So first we'll start with the market study section. So biogas is produced through anaerobic digestion process, which converted the pig manures into biogas while generating electricity, and with the remaining residues can be further used as fertilizer. So the graph here shows the biogas market value by regions from the year of 2012 to 2022. And the graph shows increasing demand for energy sources that leads to the growing demand of biogas. So next, the graph here is the total electricity sales and annual growth rates from the year of 2000 to 2030. So the trend here shows the increasing electricity demand, which indicates the biogas demand as the energy source. So next up is fertilizer. So fertilizer is actually produced from ammonia, and it is used to produce more protein-rich crops like fruits and vegetables. And In the pie chart here, you can see the global ammonia market by application in 2016. So the fertilizer application segment actually dominated the global ammonia market with over 40% of the share. Moving on to plant location. So there are a few selection factors as to how we select the most suitable plant location by considering these few several important elements like availability of raw materials, utilities, labor supply, transportation, market availability, community factors, fire and flood protection, and also waste disposal. So this is the selection marking criteria for the plant locations. For each criteria, we have the description divided into three sections, which is the poor location, 1 to 4 points, average 5 to 7 points, and good, which is 8 to 10 points. So we will be giving points for each criteria for each of the plant location itself. So this is the continuous of the marking criteria. Moving on to the proposed location marking scheme. So for each of the location, we have given the marks for the criteria respectively, and as we total up the marks, location 2 has the highest mark of 68 points. As so, our proposed biogas plant location will be at Linwood, Perak, and this figure here shows the Google Map figure of our pig farm and also biogas plant. Moving on to physical and chemical properties of feed. So the table here shows the physical and chemical properties of our feed, which is pig manure and wheat straw. Next up is the composition of biogas. The composition of biogas include methane, carbon dioxide, water, ammonia, hydrogen sulfide, oxygen, hydrogen, and nitrogen. Next up will be physical and chemical properties of product. This table shows the physical and chemical properties of our product, which is methane and carbon dioxide.
Alright, let's talk about the conceptual design for the process screening. So first we're going to talk about the alternative process road. So we found that there are three kind of different process road: the single stage, the two stage, and the three stage. So we choose the two stage because we can see the advantages compared to the disadvantages. The two stage optimize each and every AD steps, higher digestion efficiency, shorter retention time, and optimum biogas yield, which the only disadvantage is the higher investment costs when compared to the single stage, where the single stage, although it's easy to operate, but is only used for small scale. Next, we will be talking about the chosen anaerobic reaction. So the full anaerobic reaction consists of 41 steps. So here we only chose the essential one, only 12 steps. So the 1 to 3 steps will be the hydrolysis, the 4 to 6 step will be the acetogenesis, the 7 to 10 step will be the acetogenesis, and the 11 and 12 will be the methanogenesis. So for the mode of operation, there are two types of it. One is continuous, the second one will be the batch. So we did a comparison between the continuous and batch and found out that the continuous type of mode of operation is best for our project. Regarding the reactor choice, we did a comparison between the CSTR, continuous stir tank reactor, and the UASB, outflow anaerobic sludge blanket reactor. So that we found out that the continuous stir tank reactor, the CSTR, can cope with the requirement of our project and it's easier to operate. So that's why we chose CSTR as as our reactor. Moving on to the separator choice, we did a comparison between the pressure swing absorption and the water scrubber. So the efficiency for two separator is as high as 95 to 97%, But the operating temperature for the pressure swing is high, which is 70 degrees Celsius, but the water scrubber can cope at 20 degrees Celsius. And the advantages of the water scrubber is that we only use water which is harmless, low cost, and easy to handle. Mhm. So that's why we choose water scrubber as our separator to purify our biogas, to purify our methane. Alright, now will be the conceptual design for mass balance for all of the anaerobic reaction. So here is the example on how I did for the mass balance for hydrolysis only. So I did for all the hydrolysis, acetogenesis, acetal, and methanol. So inside the hydrolysis, I did mass balance for all of it, the soluble protein, the fats, and the carbohydrates. So here is the example that I did for the mass balance. Alright, so this is the mass balance for reactor 1 for our CSTR1, which consists of the hydrolysis and acetogenesis. So we can see that the hydrolysis and acetogenesis, all the product goes in, comes out the same value. This is what I did in the manual mass balance. And here is the mass balance that the icon software gave me is the same, 725 in and 725 out. For the second CSTR, the second reactor, we did add in 70 kg of hydrogen to react with excess carbon dioxide uh, to increase the methane yield for the reaction. So this is the mass balance that I did, manual one, which there's a little deficit coming out from the second reactor, but the icon software is able to balance it, which is 795 in and 795 out.
Assalamualaikum and hello, my name is Fatin. So today I will present about the economic evaluation. Economic evaluation is to determine either a project is economically feasible or not. Therefore, optimization of plant is the most important part to generate the maximum profit without neglecting the safety issues in the plant. So there are three assumptions for the calculation. First of all is $1 equal to 4 ringgit Malaysia, and the operating hours for the plant is 10 hours, and the operation days is for 345 days with 20 days of maintenance. So first of all is to calculate the economic potential 1. EP1 is economic analysis that only takes account of raw material cost and product cost. Therefore, the equation for the EP1 is EP1 equal to product value minus the raw material cost. So, the total cost of raw material including pig manure with straw, fresh water, and hydrogen is equal to 1,961,661 ringgit Malaysia. The total revenue of product, which include electricity and fertilizer, is 3,406,254 ringgit. Therefore, the value for economic potential 1 equal to 1,444,593 ringgit. Next is economic potential 2. EP2 is an economic analysis that takes into account is the utility cost. Utility cost is consists the electricity and the duty of cooler and heater. So the formula of EP2 equal to EP1 minus utility cost. So this is the EP2 for EP2 before heat integration. The total cost for the electricity is 90,454 ringgit. Therefore, the EP2 value before heat integration equal to 1,354,139 ringgit. For EP2 after heat integration, the total value for electricity equal to 37,461 ringgit. So the EP2 value after heat integration equal to 1,406,952 ringgit. Therefore, this plant is still feasible as it still have a profit. That's all from me. Thank you so much.
Now we're talking about the process flow diagram. before the heat integration for our project. So for the process flow diagram before heat integration, the pig manure is mixed with wheat straw, go into the first CSTR to undergo the hydrolysis and acetogenesis reaction, comes out, addition of hydrogen into it before going into the second CSTR, so to increase the methane yield. So the digestate comes out from the bottom of the second CSTR, goes into a solid liquid separator to separate out the water and the fertilizer. The fertilizer is then sold to increase our profit. So the vapor gas consists of biogas, water vapor, and some of the minor things. When we cool down, go into the vapor liquid separator to separate out the water from the biogas. The biogas will go into the water scrubber, and all the excess water will mix with extra water from here and go into the scrubber to scrub off the H2S in the biogas. After scrubbing the biogas, pure methane will come out here, and then the wastewater will go to third party as for treatment. Now we'll be talking about the process flow diagram after the heat integration. From here we can see that there's an addition of heat exchanger to exchange the heat to save up some utility costs for this project. The detailed one I will be explaining in the heat integration part. Now we are talking about the heat integration for our process plant. So this picture here shows the plant before heat integration. So here shows the plant after heat integration. So we can see that the heater is added in, and then the cooler. So the heat exchanger is used to minimize the utility cost of the heater and the cooler. This is the heat cascade for our plant, which 20.38 kilowatt is the minimum hot utility, and then the 3.73 is the minimum cold utility, which is used in our plant design.
Assalamualaikum and hi, my name is Nurul, Aina, Imanina binti Arijan, and I'm going to talk about process control. Process control is an essential in any industrial process to achieve well-defined objectives, where the main objectives of implementing process control is the safety of materials used, environmental protection, equipment protection, and etc. 6 design steps of process control system. Firstly is to identify the control objectives such as the temperature, level, pressure, composition, and flow rate. Next is identifying and classifying the process variable and developing model. Next, selecting the appropriate control configuration by depending on dynamic behavior, available measured PV, and required control performance. Next, selecting the appropriate controller type, selecting the appropriate instrumentation and preparing the PNID. Lastly, tuning the control, which all depends on control configuration. 7 fundamental control strategies. First, feedback control. MV is adjusted based on CV. Second, cascade control. The inner loop controller obtains its set point from an outer loop controller. Feed forward control. MV is adjusted by DV. Ratio control is keeping a parameter in proportion to another same parameter from different inlet. Split range control, where 2 or more manipulated variable is adjusted based on a single control variable. Override control, where a single manipulated variable is adjusted based on 2 or more control variables. 7. Advanced control. There is several types, which it will not be covered in this presentation. Summary of control requirements. First, mixer is basically to manipulate the discharge flow rate going out of the mixer by controlling the liquid level inside the mixer using the cascade control, where the inner loop is the flow rate and the outer loop is the liquid level, where M101 is to maintain liquid level by liquid feed mixing of pig manure and wheat straw, while M102 is to maintain liquid level by liquid feed mixing of hydrogen liquid and the product of the first CSTR, while the M103 is basically to maintain the liquid level by adequate feed mixing of water and liquid from the first and second separator. Anaerobic digester, which is the CSTR, is basically to manipulate the amount of fluoride going into the reactor by controlling the value of pH at the outlet of the reactor using the feedback control. But R101 is to maintain pH at an acidic environment higher than 7, while R102 is to maintain pH at optimal condition between 7 and 8. Separator is basically to control the amount of excess water going out of the separator by manipulating the amount of fluoride going out of the separator by controlling the liquid level inside of the separator. And second separator is to control the amount of condensate water going out of the separator by manipulating the amount of fluoride going out of the separator by controlling the liquid level inside of the separator, and to control the pressure going out of the separator by manipulating the amount of fluoride going out of the separator by controlling the pressure inside the separator. We're both using the feedback control. Okay, water scrubber is basically to control the amount of wastewater going out of the separator by manipulating the amount of fluoride going out by controlling the liquid level inside the separator, and to control the pressure going out of the separator by manipulating the amount of fluoride going out of the separator by controlling the pressure inside the separator, which uses the feedback control. Heat exchanger basically is to maintain the temperature at 25.9 degrees by manipulating the amount of steam fluoride going into the heat exchanger by controlling the temperature at the outlet of the heat exchanger using the feedback control. That's all from me. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum and very good day. My name is Muhammad Zahir bin Shah and I am presenting the safety and loss prevention section of this presentation. Throughout the course of the project, we have carried out several process hazard assessments which serve to provide a clear analysis of each of the hazardous elements that may be present in the proposed chemical processing plant. One of the PHA strategies utilized in this project is hazard analysis, which can be described as a systematic method of assessing complex process facilities or operations, which can then be used in identifying actual and potentially hazardous elements in a plant's general activities. Hazard is commonly used by process safety engineers as a technique to study process hazards and make recommendations accordingly to eliminate or mitigate the risk of the hazard to a tolerable level. Furthermore, hazard is also useful in providing a universal assessment method which can be utilized in most process facilities regardless of the processing operations carried out in the plant's premises. Hazard identify risks of the hazards based on the deviations of the parameters from the design values, which is specified in the PNID. A study note in a hazard analysis refers to a point in a particular process whereby hazard evaluation would be carried out. By using specific guidewords, the deviation of a critical parameter can be determined, in which the safety engineers would analyze the possible factors of the incident as well as any potential consequences of the scenarios. Safety recommendations can then be proposed to mitigate the potential problems to the system. In this project, the study notes selected for the hazard assessment are as provided in the table. Each of the equipment are attached to the reactor R102, which contains most of the hazardous chemicals during the plant's operations. The first study node identified for the hazard analysis of the proposed chemical processing plant in this project is mixer M102, whereby the critical parameters of this equipment include flow, pressure, and temperature. One of the potential deviations with respect to flow refers to a larger flow of fluid in the pipelines, which goes under the guideword more. This scenario may be triggered by a flow rate control malfunctioning during operations, which would then result in the overloading of reactor R102. To prevent this problem, the plant operators are advised to replace the flow rate controller during maintenance. Next, for pressure, one of the potential deviations include pressure being too low in the process unit, which goes under the guideword less. This is caused by pipeline leakage, which would then cause the chemical backflow into reactor R102. To mitigate this issue, the plant operators are advised to repair the pipeline as per required. Last but not least, for temperature, one of the potential deviations include the outlet temperature being higher than 25 degrees Celsius, which is the design values as specified in the PNID. The possible cause of this is due to minimal heat loss in the mixture, which may cause potential damage to other equipment in the system. To prevent this issue, the plant operators must install a temperature control valve in the system. The second study node for the heads-up analysis in this project is pump P103. Similar to the mixer earlier, the critical parameters of this equipment are flow, pressure, and temperature. For the flow rate, one of the possible deviations refers to a larger inlet flow of fluid which goes under the guide word more. The possible cause of this scenario is control valve failing to close during operations, which may cause the pump to be overloaded. To prevent this issue, the plant operators must repair or replace the control valve during maintenance. On the other hand, for the pressure, one of the potential deviations is no change of pressure of the fluid across the pump, which falls under the guide word no. One of the factors of this scenario is the pump being damaged during operations, which may cause the fluid to take a longer time to be transported in the system. To mitigate this issue, the plant operators must install a spare pump in the system. Lastly, the third study node for the heads-up analysis in this project is heater E102. The critical parameters of this equipment are flow and temperature. One of the potential deviations with respect to flow rate is there's no flow of fluid in the pipeline going into the heater, which goes under the guide word no. One of the potential factors of this problem is there's a pipeline rupture during operations, which would result in a no supply of fluid across the process units. To fix this issue, the plant operators are advised to repair the damaged pipeline. On the other hand, for the temperature, one of the possible deviations include the outlet temperature being too low across the heater. One of the possible causes of this issue is there's fouling on the equipment during operations. This may result in the reactants not being sufficiently heated before going into reactor R102, which will reduce the efficiency of the overall process. To mitigate this problem, the plant operators are advised to conduct routine cleaning on the internal part of the equipment.
Conclusion. The biogas production plant is designed with loading rate of 15,000 kg of manure and 2,400 kg of wheat straw per day. So we produce a total of 5,019 kilowatt hour of electricity. Revenue of our fertilizer is around 600,000 ringgit and the profit of biogas will be around 2 million ringgit. Recommendations. So our recommendations will be more hazard assessment should be conducted. For example, like failure mode and effect analysis (FMEA), hazard identification, hazard, Dow Fire and Explosive Index (FMI), Dow Chemical Exposure Index (CEI). Apart from that, more workshops and tutorial classes should be held as to teach us on how to actually use the icon simulation and also how to accurately draw the PFD and PNID.